Have you ever wondered what magic happens when you press Citymapper's Go button? How does Google Maps find the route home faster than you can blink? Let us look at an example to help us answer these very questions. London has grown over centuries, and a map of it can seem overwhelming at first. With so many roads, routes and rivers, finding an efficient way to travel across the city is not easy. The first diagrammatic map of London's rapid transit network was designed by Harry Beck in 1931. He realised that for the average traveller, the geographical locations of the stations are largely irrelevant. Instead, only the topology of the tube matters. Even with the simplified schematic of the tube, it's not obvious which route to take. In fact, there are infinitely many ways to get from one station to another if you're willing to go in circles. Instead, we could get a computer to do all the heavy lifting for us. But how do we turn this complicated collection of colourful curves into something that a machine could understand? The answer is graph theory. A graph is a set of individual objects or vertices that are related to one another. Each vertex has a unique value. When two objects are linked in some way, we can draw a line between them called an edge. To make this graph more useful, we can store additional information about each node and each edge. Each edge is given a length, or a weight, that represents the time taken to travel between the two stations. Sometimes the relation between two objects is not symmetrical. We can represent these kinds of relations as a directed edge by drawing an arrow on the end. After spending hours individually identifying every station, I painstakingly penned a Python program to process the map. TfL is kind enough to provide interstation travel times, which I used as the weights for my graph. Let us take a look at the imported graph from the computer's perspective. It certainly resembles a tube map. Of course, the graph does not store any information about the layout of the map, which is why Watford appears in central London and Heathrow is in the east. Just as the official tube map is only a diagram, this graph has only the information that is relevant to us. Now all we need is an algorithm to find the shortest route. Humans are rather good at finding short and, sort of, efficient paths, so let's take some inspiration from them. I asked them to draw a route from Richmond to Harrow, which is a cumbersome route requiring at least 2 changes. It appears as if they roughly imagined a straight line from A to B and tried to find the closest approximation to the line. It's particularly clear in the third clip, where a wonky route through central London would be faster, but is not obviously so. DFS is the first and simplest search algorithm that I implemented. It stands for Depth First Search. DFS uses a stack structure to keep track of the stations. It takes a plate from the top of the stack and replaces it with a plate for every unvisited neighbour. The process repeats until we find our target. This results in an algorithm that goes as far down each line as it can go before backtracking. Just like a human, the algorithm is not complicated and results in a path that is not necessarily the fastest one. Clearly no sane person would think of getting from Richmond to Harrow via Canary Wharf. To avoid redundant searching in the wrong parts of town, we can use BFS instead. Unsurprisingly, it stands for Breadth First Search. Unlike DFS, it uses a queue structure to keep track of the stations. For every station it visits, it appends the neighbouring stations to the back of the queue. BFS is guaranteed to find the shortest path if measuring path length solely by the number of stations on it, and it visits fewer stations overall. Etzrich Dijkstra was a 20th century Dutch computer scientist. Although he did not become famous for the dining philosopher's problem, the breakthrough of his career was the far less catchy-sounding Dijkstra's algorithm. Let's listen to what Dijkstra had to say about it.
It is the algorithm for the shortest path, which I designed in about 20 minutes. One morning I was shopping in Amsterdam with my young fiancée, and tired, we sat down on the cafe terrace to drink a cup of coffee, and I was just thinking about whether I could do this, and I then designed the algorithm for the shortest path. As I said, it was a 20-minute invention.
His method is not too dissimilar from BFS, but it takes into account the weight of each edge, and finds the shortest path by total length. One major drawback of Dijkstra's algorithm is that it still visits some nodes which, as a human you can clearly tell, are unnecessary for finding the shortest route. What if the algorithm had a rough idea of where to go? This is where A* comes in. It is seen as an extension to Dijkstra's algorithm, and it uses heuristics to guide its search. That means that the computer judges which node to explore next based on a variety of factors, including the weight of the edge, the distance of the node from the target, and whether it has been explored before. In fact, this informed search algorithm is so popular that A* and its variants are still used in many applications to this day, from video games to travel planners and even in virtual assistants. Google Maps, for example, uses A* with some handy time-saving tricks. By pre-processing the graph, their algorithm identifies unique shortest paths and remembers them as shortcuts. This is significantly faster than calculating the shortest path from scratch every time. With 7.5 minutes of pre-processing, the search time is reduced to 0.56 milliseconds. With 2.5 hours of pre-processing, the search time is slimmed down to a mere 1.7 microseconds, which is over 3 million times faster than Dijkstra. Hands down, Citymapper and Google Maps are faster and better than my Python visualization program could ever be. How could my code account for unexpected delays, or waiting for trains, or ridiculously long interchange times? Perhaps one day, while sitting in a cafe in Amsterdam, you'll be the one to come up with a new and better shortest path algorithm.